Welcome to the second lesson in Session 1 of inverse functions and equations. An inverse function is a function that reverses another function. Now, to help support that definition, we're going to use a function that we defined in the previous lesson, and that's f of x is equal to 3 to the x power. And we're going to go through the process of finding the inverse function of this function. Now, we remember from the previous lesson that if we had an exponential function, we would set up a t-table, select a handful of values for x, preferably a couple values on each side of the origin, and then we would substitute those values in for the x value of the function. That would produce a corresponding output, which is our y value. Once we get the list of x and y values, we can then plot those values and graph our function. To find an inverse function, we have to switch the values of x and y. So instead of y equals 3 to the x power, we're going to trade x and y, and we're going to call it x equals 3 to the y power. Now, we're going to use the same thing. We set up a t-table, but the values of x and y get flipped. So if my original function, which I often call my parent function, is given as y equals 3 to the x, my inverse function is x equals 3 to the y. So notice the values of x and y have now traded places. That holds true in the t-table. So when I look at the t-table, from my parent function to my inverse function, the values that are in my x column are now going to be expressed in the y column. And the values that are expressed in my y column in my original function are going to be expressed in the x column in my inverse function. Now we can plot those lines just the same, and you see this is what our function looks like. Notice that the value of x will never get less than 0. It'll get infinitesimally close to the y-axis, but will never touch the y-axis. It will increase dramatically as x is small, and as x increases, it flattens out. But what if I wanted to find some additional values for this inverse function? So can I start with the value of y? Y is equal to 3. Well, I can plug that in. X equals 3 to the y, so if I plug a 3 in for y, I can find a value for x. So if I plug in any value for y, I can always produce a value of x. So in this case, the value of x would be 27. Now, if I have an x value, 81 is equal to 3 to the y power. Well, this will work because 81 is a perfect exponential root. So I know that 3 to the 4th power is equal to 81. However, if I have a value of x that's not a perfect exponential root, I run into a problem here. I don't have a method for solving for y in this case. 15 is equal to 3 to the y. Now I can't add, subtract, multiply, or divide to isolate the variable because the variable is an exponent. So what we do is we use logarithms. The inverse of an exponential function is called the logarithm. And in this case, the logarithm would look like this. The inverse function of f is equal to the log base 3 of x. Important thing to catch here is the inverse of an exponential function is called a logarithm. Let's see how this works. So we're going to analyze a couple of graphs. So we're going to use our parent function. Our original function is f of x equals 2 to the x power. So again, we have a model for exponential growth. And here is the x and y. Here's the t-table, and here's the graph of our parent function. Now, y equals 2 to the x power. If I trade x and y, in this case I get the inverse function of x is equal to log base 2 of x. And we'll get into the notation of logarithms in a future section. So for the t-table, I just reverse. The values -2, -1, 0, 1, and 2 that are in the x column are going to be expressed in the y column for my inverse function. And the values in my y column for the parent function are expressed in the x column for my inverse function. So when the x and y values get flipped, this is what my function will look like. So again, I have my parent function, which is the red curve, which starts off really small, close to the x-axis, and as x increases, my y values increase dramatically. My inverse function is the blue curve that starts off infinitesimally close to 0 and increases dramatically and then flattens out as x increases. Now the graph of a function and its inverse are always going to be symmetric about the line y equals x. So you see, as I graph the line y equals x, which is a straight line that passes through the origin and has a slope of 1, so this green line right here, my function and the inverse are going to always be symmetric about that line. That wraps up our lesson. Feel free to email us if you have any questions. Good luck on the quiz.